In this clip, we're going to combine two attributes at seismic resolution to highlight the reservoir. This is the continuation of clip 1, in which relative lambda rho and relative mu rho, shown here in tracks 1 and 2, are cross-plotted and color-coded by the gas volume. These attributes are then rotated relative to the coordinate axis to align the reservoir points along the x-axis. This results in maximizing the energy in the x-axis while minimizing the energy in the y, and giving a better image of the reservoir in the x-axis. The analysis at seismic resolution will include normal incidence and gradient. The attributes in time will be compared with those computed in depth. Next, we are going to QC the attributes at seismic resolution before doing the coordinate rotation. Let's start by looking at the pre-stack synthetic and the attributes generated. Here we have in track 2 the attributes being evaluated, in this case normal incidence and gradient, and in the third track we have the pre-stack synthetic computed from 0 to 45 degrees every 1 degree. The bandwidth used is 5, 12, 50 to 75 Hz. Some observations. Let's start with the attributes in the log plot. We see here the lowest trough does not correspond to the top of the reservoir as we would expect, although the base of the reservoir matches or corresponds to a peak as expected. Let's now take a look at the scatter plot. In the scatter plot, we show the same attributes as in track number 2, and the magenta points correspond to the pay points in the petrophysical evaluation track. When we compare this with the equivalent in depth, we see that the match is not as good as we would expect. And what we're going to be doing in the next part of the exercise is to verifying that the differences in between the attributes in depth and in time are associated to resolution or to tuning, as well as the fact that the trough in the normal incidence does not match with the top of the reservoir. This is the summary of the resolution analysis done in clip 2, which can be found on TraceSeis' website. For the analysis, we are zooming from 2.08 seconds to 2.14 and showing the normal incidence trace in both the attributes and in the angle gather tracks. The objective of this part of the exercise is to show or to verify that an increase in acoustic impedance is going to result in a positive reflection coefficient, and a decrease in acoustic impedance is going to result in a negative reflection coefficient. To be able to do that, I have created here a normal incidence trace with very high frequency. I have used here upper frequencies of 4000 and 5000 Hz, which I can do because I am using a sampling interval of 1/10 of a millisecond. This would be equivalent to having no wavelet. To continue with the analysis, I include here a plot in depth showing the impedances, density, and in the right the petrophysical evaluation. So we have data in depth in the right and data in time in the left. I am now going to select a point here at the top of the reservoir where the acoustic impedance is decreasing, and show that this results in a negative reflection coefficient, or red color. We're going to take the next point, which is an increase in acoustic impedance, which goes to a positive reflection coefficient, or blue color. Let's take one more point down in here. This is a decrease in acoustic impedance, which goes to a red. So I think that with this we have verified that the program is producing the results that we would expect, and we conclude that the fact that the lowest normal incidence value not matching the top of the reservoir is associated to tuning or to resolution. Next, we're going to do a similar analysis using the crossplots. In this part of the analysis, we're going to compare attributes computed in depth at well low resolution with those computed in time at seismic resolution. The first crossplot to the left is the normal incidence and gradient crossplot computed in depth at well low resolution, and the next to the right are the equivalent attributes computed at seismic resolution with a very broad bandwidth of 4000 to 5000 Hz as the upper limit. This is done to get the equivalent attributes to those computed in depth, and we see that the match is fairly reasonable. From there onwards, we're going to reduce the bandwidth until we get to the seismic bandwidth. This is what we would expect from the seismic data. The lower row is similar analysis, but in this case using relative lambda rho and relative mu rho. The crossplot to the left are the attributes computed in depth at well log resolution, and the first attribute or the next crossplot to the right are the same attributes computed with very high frequencies, with the idea of matching the data in depth. We see that the match is reasonable. From then onwards, we decrease the frequencies, in this case a high limit of 1000 to 2000 Hz just for illustration, until we get to the attributes that we would expect at seismic resolution with a high frequencies of 50 to 75 Hz. These are the attributes that we're going to use to do the coordinate rotation. We are now ready to rotate the data. Let's start with the scatter plot that we just created, and then plot the data in time. So this is the data in time, in two-way time. The second track is relative lambda rho and relative mu rho, the same data that is cross-plotted in the scatter plot below. Let's now rotate the data, let's say 130 degrees. Create the scatter plot. That produces the effect that we want, which is to align most of the anomaly in the x direction. And let's now do the synthetic data plot. Here it is. Now we see that the energy in the x-axis, the blue line, is highlighting most of the reservoir, and it's interesting to note as well that the zero crossing where the anomaly starts is at the top of the reservoir, and again the zero crossing where the anomaly finishes is at the base of the reservoir. And with this we finalize this tutorial. Thank you.